Let's look at a differentiation problem. Say we have a function y equal x to the 3 over x. The problem asks to just find a derivative, but I went ahead and did a little bit more analysis just to add some more ideas to the problem. But when you look at something like this, the first thing that comes to mind is to change the base. So for instance, we can change the base to the natural base and get e to 3 to the x minus 1 times log x. So again, the changing of the base just simply transforms the problem into something that we understand as far as calculus. So when we want to compute y prime, of course the derivative of the natural exponential is itself times the derivative of the power. And so of course we have a 3 here, which we can factor. Constants always come out, I always do that. And then we want to differentiate x to the minus 1 times log x. Okay, that's just the product rule. So we'll have 3 times the exponential factor, and then of course the derivative of x to the minus 1 is negative 1 over x squared, and then we have times log x. And then of course the derivative of ln of x is just 1 over x, so we get 2 copies of 1 over x. And so now, if you will, you can just factor the 1 over x squared, and then of course this term here, e to the 3 x to the minus 1 log x is just the original function. So we have 3 times x to the 3 over x divided by x squared times 1 here minus log x. Now, of course, if you wanted to, you could go ahead and replace x to the 3 over x with y, but that's fairly useless. It just rewrites things, but it doesn't help you so much with the calculus. So that would be one place you could stop, or you could stop here. Well, clearly, if we leave it in this form, we can use the laws of exponents and just subtract 2 from 3 over x. So you can write 3 over x minus 2x over x to get a common denominator. And then that would just give you 3 times x to the power 3 minus 2x divided by x times 1 minus log x. And so that would be a form of the derivative. So what I noticed here, and it seemed to be a very simple process at this point, we see here that this particular function makes no sense at 0, and it also doesn't make any sense for negative powers, or excuse me, for negative real numbers, because then you're going to be taking radicals of negative numbers, especially even radicals, and that makes no sense. So the domain of this function is just 0 to infinity. So changing the base kind of helps you to see that. And now what you can see, if we've got any critical numbers, that's where Fermat could enter in. So notice here that this portion here is never 0. This is just a power function with positive x's. This is always positive. You can go ahead and look up here and see that that's going to be the case. And then of course this can be 0 when x is equal to the natural base. So this actual derivative is 0 if and only if x is equal to e. So now you can say, okay, well, we start at 0 and run out to infinity. So we have this critical number here, and of course it e over 2, which is in this range, this factor will be positive, so this gives us an increasing function. And then of course greater than e, we have a decreasing function. So basically the function evaluated at e, that is e to the 3 over e, has to be a maximum. There's no other classification for it, because we increase and then we decrease, and that's it. There are no other items to consider. So that at least tells us that we have some very simple calculus going on. Now the only other issue is just to consider what's happening as x approaches 0 from the right, and what happens as x approaches infinity. Well, the nice thing about this is that when you look at this particular function here, changing the base, this gives you something to analyze. This is just ln of x over x. The 3 doesn't matter, it's just a constant. And so I can look at this and say, okay, well, as x is approaching 0 from the right, this is becoming positively infinite, and this is becoming negatively infinite. So that's just negative infinity. That's not even indeterminate. And so if that's the case, so we see if that, for instance, this power is approaching negative infinity, then just like in a standard exponential function, e to the 3 times x to the minus 1 ln of x will approach 0. So that's just basic analysis there. That's just like thinking about a standard exponential function where the x-axis or y equals 0 is an asymptote. So that clearly tells you what's going on as x approaches 0 from the right. So basically we're coming in this way to 0. And now again, and this is something you'll see more about in calculus too, ln over x, ln x over x, what happens to that as x approaches infinity? Well, the ln of x increases, but it takes its time. The x will overpower that. So this particular expression will approach 0 as x approaches infinity. Therefore, this term, if its power approaches 0, then this will converge to 1. Again, a very natural characteristic of the exponential function. So what we're seeing here is that we're undefined at 0, we increase to the maximum e to the 3 over e, and then we decrease and we approach the horizontal asymptote y equal 1. Now I did not compute the second derivative, so I'm not really sure about the concavity here, but that is a basic rendering of the function graph just utilizing the first derivative, the domain, and the limiting processes that basically rely upon standard college algebra and pre-cal. So this problem turned out to be a lot more interesting than I thought. But again, just remember, you don't have to guess about these functions. You simply write them by changing the base into a form that you understand. That is, we understand the calculus of this function, and we can easily get the maximum here. And then with a little small analysis here, we can figure out what happens at the extreme, so to speak. So take this example as a good example for physics and engineering when you have interesting functions and you're trying to figure out exactly what they're doing. And we're done.